Hi, I'm Jordan Baton from Limit State, and today I'll be explaining how to combine multiple components in order to complete advanced optimizations in Peregrine, the structural optimization plugin for Grasshopper. After a solution has been calculated using the layout optimization component, it can then be post-processed using multiple components in order to achieve a simplified or more usable solution. This is the raw solution calculated using the layout optimization component with a high nodal density. Post-processing components can be connected using the solution data inputs and outputs to the components. Now I'm going to use the geometry optimization component to allow the nodes to migrate away from their Cartesian coordinates. This will likely reduce the required material volume and produce a slightly more simplified layout. After this, I'm going to use the crossovers component to ensure that nodes are created in all instances where the elements cross. Between every post-processing component, it is good practice to run an additional geometry optimization in order to achieve the optimum solution. Next, I'm going to use the merge joints component to slightly simplify the solution. If the component is clicked, it is possible to preview the merge radius assigned to the solution. All instances where two circles cross will be merged into a singular node. This is the solution after merging nodes, and this is the solution after an additional geometry optimization, which is 2.5% lower in volume. This highlights why it's beneficial to complete an additional geometry optimization after each post-processing step. Now I'm going to use the filter component in order to remove some of these smaller members. The filtered members are highlighted in yellow when the filter component is previewed. Once again, this component is followed by an additional geometry optimization in order to achieve the best solution. The new solution looks good, however still has a relatively slender member compared to the others. I'm going to use an additional filter component to remove this. The solution is now much simpler than the raw solution calculated after the layout optimization and requires an almost identical volume of material. The final post-processing component that should be used is the stabilize component. This ensures that the solution is linearly stable under the specified loads. For this component, I'm going to set the load factor to 3 to account for eccentricities incurred during construction and second-order effects. The stabilize component should be the final post-processing step, as other components may introduce a state of unstable equilibrium once again. In this example, the structure is linearly stable, so no change happens. Thanks for watching. For more information, visit our website.